this session. I'm noticing a lot of people missing from the class, huh? All right, good. So we're kind of closing off our course, and what we'll be looking at now is the reverse of differentiation, which is the process of integration. Right? So differentiation was, you have a function, you have some function. Okay, let me see if I can move this thing away. You had a function, let's say y equal, okay, x squared. And when you differentiate this, you get dy dx equal 2x, right? So that's the forward process of differentiation. Now, what if you get 2x, right? dy dx, or the derivative of some function is 2x. And you want to know what's the original function, right? What's the original function? Well, that's the process that we're referring to as integration, right? You're trying to put back together um, the original function, right? Um, so this entire process of doing the reverse of differentiation is what we call integration, right? There is a reason I want you to draw your attention to is this word indefinite integration. Why we are talking about this first? We're going to come to integrating functions when we're going to be able to, at the end, have a definite integral and to even evaluate it. But for now, we're talking about, well, getting what we call indefinite, right? Meaning you're not certain. You're not 100% certain, right? What the original function was. And I'll explain why. I'll explain why in just a moment. All right. Look at these two. Look at these two functions on top here. X squared plus 1 and x squared minus 7. Both of these functions, and of course a million others, right? If we were to differentiate x squared plus 1, we get 2x. If we were to differentiate x squared minus 7, we also get 2x. So when you integrate 2x, well, you could get, it's possible that the original function is x squared plus 1, and it's possible it's also x squared minus 7. As a matter of fact, there are an infinite number of possibilities, right? There's an infinite number of possibilities, and therefore, what happens is that because we're not certain, right? This is what we do, and it's the reason why we call it indefinite integration, right? So we have, okay, all right. Let's put it this way: dy dx equal 2x. Good. So if we were to do what we call separating the variables, so we multiply this across there, right? So you have dy equal 2x dx, right? So we got the y's over here, we got the x's over here, and we integrate both sides. But of course, you don't know how to integrate yet, right? But all right, I'm just going to do it for you. So there's like a 1 here. When you integrate 1 with respect to y, you get y. Now, because you're not certain if there was some number here, some number there, you're going to put y plus, all right, let's go with k subscript 1. Now, when you integrate over here 2x with respect to x, you get x squared. And then again, because we're not certain what might have been at the end here, you're going to have k2 there, right? So we have a constant over here, we have a constant here, over here. But we don't want to have constants all over the place. So what we do, we take the constants to one side, and you end up writing y equal x squared plus, and we probably use a big K, as you're seeing here, right? A big K. And we call this an arbitrary constant, right? The constant of integration is an arbitrary constant. What it means is, what that word means, right? Arbitrary carry the idea of not really belonging to one side, right? So we don't want a constant over here and then a constant over there. So we just merge the two and we name it, you know, we give it the letter big K, right? Or the unknown big K. And we say that, look, this is an arbitrary constant, meaning that it doesn't belong to either side exclusively, right? It could have been over here, but we choose to put it here, right? And that's why every time you integrate, when you're doing what you call indefinite integration, you integrate something like this, you have x squared plus K. You just add on a K at the end there. Anything you integrate, if you're dealing with indefinite integration, in other words, there's no way for you to evaluate this value, this of K. You just put a K at the end, right? Even in the textbook, when I give you a problem and you check the answer, something you don't see a K there. But whenever you integrate, you have to put a K. But if it's textbook in their answer wouldn't put K all over the place, right? You must be sensible to know that and say, man, sorry, how you tell me the answer is this plus K, but at the back only got X squared, you know? They don't write K over and over and over. They know that you're supposed to know that the constant of, what am I talking about? The constant of integration has to be at the end there, right? You think you get why we're having that K at the end there? As we said, when we integrate 1 with respect to y, it is possible it could be y, it could be y plus 1, it could be y plus 2, it can be y minus 1. It can, it can be all kinds of things. But because we don't know what that number is here, this constant here, we put K subscript 1. We just put in a constant. Over here, when we integrate 2x, it's possible that, well, it was not just x squared, it's probably x squared plus 1, x squared minus 1, x squared plus a half. We don't know what was there, right? So we put K subscript 2. Now, instead of having K's all over the place, we put all the constants to one side and we call it, we say that this K is an arbitrary constant, right? It kind of represents those two constants that should have been there. Doesn't belong to any one side. Right? The teachers of all people should understand the use of the word arbitrary. When they're striking for more money, they always end up at arbitration. And the arbitrator, well, he just violated the meaning of the word. He always sell out. But the arbitrator shouldn't belong to any one side, you know, they should be a neutral person. All right. Good. So I hope I'm not getting any feedback from the class as to whether they're getting what I'm talking about. So, all right, good. So now we want to introduce ourselves to some integration techniques now, because we have all kinds, and in this course, we can't even scratch the surface of the different families of functions that we need to integrate, right? So this is just an introduction. Right? We can't do that in one day, or not even 1 week, not even one semester, right? Integration is a big thing. And those of you who are going to end up doing what we call Calculus 2, some of you, the teachers, and so should be able to do that course next year. You'll see how far more we'll go with both differentiation and more so integration. That course is a extremely heavy course in integration, right? And I guess they're now bringing engineering to Borbies. Those people, they use differentiation and in particular integration a whole lot in their studies, you know. So they have to do calculus and especially the practical application of it so much more. Good. So let's start with some. And again, we're not doing anything from first principles. We're basically going to use some standard formulas, which should be very easy for you, right? And what would make it, I mean, integration is always a hard thing to think, that reverse logic, thinking in reverse, not backward, but reverse is so very difficult, right? It's very difficult for people to do that. And that's what integration is about, piecing together back the pieces to see if we can get as close as possible to the original function, right? So here you have, this is kind of like a standard formula. If you have x to the n, and you are integrating this with respect to x, that's why you have the dx there, right? It means you are integrating x to the n with respect to x, right? This is the integral sign there. It's like an elongated S, like, you later on, or if you do any reading about the history and so of calculus, you will see where these symbols come from. Because later on, I think next week, maybe we'll talk a little about applying integration to find areas, and then you'll see where this S-shaped symbol and how it came to be the symbol for integration, right? And you can always YouTube that sort of thing, or ask some AI about a little bit of history and read about it, huh? Good. So this is a little formula, right? Notice what they're doing. They're doing the very opposite of what we were doing when we were differentiating. When we were differentiating, what were we doing? We're taking the n on top there, multiplying the coefficient in front of x, and then we were reducing the power by 1. We're not doing that here. We're doing the very opposite, right? Remember, we were taking 1 from the power last, but in this case, you're going to add 1 to the power fourth, right? And then you are going to divide the number in front of x. In this case, it's 1. It doesn't have to be 1. It can be any constant. You're dividing the number in front of x by that new power, right? N plus 1. And that's what you're seeing here. So that's the very opposite of differentiation. Very opposite. You're doing the exact opposite of what you would have done in the power rule. You remember that power rule? Well, this is the power rule for integration. Right? And you do about 10 of these and it becomes second nature to you, right? It comes with practice, huh? So here are some examples, right? So we have the integral of x to the 7. So we add 1 to 7, we get 8, and we divide the number in front, which is, in this case, there's a 1 in front here, right? We divide it by our new power 8. And don't forget, plus k, because we're not certain if there was a number at the end here, right? There could have been a number there, so we put plus k. Same thing here. X to the minus 4, add 1 to the minus 4, you get minus 3. And then you divide the number in front of x. In this case, it's 1. As I said before, it doesn't have to be 1. But in these examples, they seem to like the number 1. And you divide that 1 by the new power, which is minus 3. Again, plus k. Right? Almost, once you're dealing with indefinite integration, you'd have to have that k at the end there, right? So I can trick you in the multiple choice, I can give you the integral of this thing is this here, right? I can probably don't have the k. I mean, indeed, technically, the integral of this could be this, right? But remember, in multiple choice, you want the best answer, right? The best answer, not just one possibility, right? Don't forget that. I wish I had a chance to discuss the test with you that you did already last week, I think. But there's some people who I think have to write the test. So I have to go. I don't know when I'll get a chance to give them the test. They gotta really plan up with me someday. And let's have that test run off. Anybody in the class that didn't write the test today? All right. So we have, okay, again here, I guess the writing here is very fuzzy. X to the half, this is, right? The integral of x to the half. So you add 1 to half, it becomes 3 over 2. You divide the number 1 by 3 over 2, you get 2 over 3. So you have 2 over 3 x to the 3 over 2 plus your k. Right? Simple as that. Good. So let's go now. Let's try some others. Well, this is just a what would I say? It's like something that followed from the previous law, right? Or the previous rule. You integrate c, you get cx plus k, right? Just like when you differentiate cx, you usually just drop out the x and you get c. So you're doing the opposite now, right? And don't forget your k at the end here. And here they kind of put in a number in front of x now. Just now we were only having 1 there, right? So if you were to have a number in front of x other than 1, well, you apply the same rule. This is not an extra rule, really. It's just the first one you learn, right? So you add 1 to the power, it becomes n plus 1, and then you divide the constant in front of x by that new power, which is n plus 1, right? And don't forget your k at the end here. So these are some little rules. And again, if you do a couple well of these, it becomes second nature to you, right? It becomes second nature to you. Good. If you have a string of terms together, just like in differentiation, if you have a sum or difference or like a polynomial set out, and you have to differentiate, what did you do? You differentiated each term, isn't that so? But that's what you do here as well. When you're integrating, you just integrate each term, right? So the integral of all this whole string of terms with respect to x, you just integrate each term using the rules we just talked about, right? Well, so now we have, okay, another family of function here. This is what we refer to as the function of a function. And if you remember, we were using the chain rule and all of that, right? So how do we integrate this sort of thing, right? I'll skip over this slide. So it's just illustrating. Here's the formula. So this is your formula here. The integral of ax plus b to the n power with respect to x, the integral of that, this is what happens. Oh, and by the way, this formula doesn't work if you have like a ax square here, right? If there's a power there, no, it doesn't work. There has to be a linear function inside there, right? You all know what a linear function. It can't have some power of x, like 2 and 3 and 5 and whatnot. The power got to be just 1, right? Ax plus b, that's the form. And that's the thing. Of course, you can have a minus sign there, right? Yeah, so what do you do? Right? Note what happens. You add 1 to the power. Right? The bracket remains the same. Don't ever trouble what's in the bracket. Just like the differentiation. You never trouble what's in the bracket. But in front here, you divide by, what do you divide by? The new power, which is n plus 1, but you have to do an extra step, times the derivative of inside the bracket. In this case, the derivative of in the bracket is a, right? So that's the extra bit you have to remember there. Right? So you take the what's in the bracket, never trouble that. Increase the power by 1. And whatever number is in front here, it doesn't have to be 1. In this case, there's a 1 here. But if it's any other number, 2, 5, 10, minus 1, you don't care. Whatever the number is here, it doesn't have to be 1, as I said. You divide it by the new power times the derivative of the bracket, which is a in this case. Right? We see some examples here. We have to integrate 3x minus 8 to the 6th power. What do? Put back the bracket. Never trouble that. Oh, and I forgot the k at the end, right? Even I am forgetting the k. So you write back the bracket, you raise the power by 1. Right? You put your k. And in front here, you divide what is in front of the bracket. In this case, it's 1. As I said, it doesn't have to be 1. It can be any number, right? You divide, and in this case, it's 1. You divide 1 by the new power times the derivative of in the bracket, which is 3, right? And of course, you simplify this. This is 1 over 21, 3x minus 8 to the 7th power plus k, right? And these here is the same thing, right? You got 2 minus 5x to the 9th power. You're integrating that with respect to x. You write back the bracket, raise the power 9 by 1, you get 10, put your k, and in front here, you divide the 1 that is in front of the bracket, you divide it by your new power 10 times the derivative of which is of what is in the bracket. In this case, notice it's minus 5. So the answer is going to be minus 1 over 50, bracket 2 minus 5x to the 10 plus k. Right? Following that so far? Let me leave it for a moment. I hear nobody saying nothing. Well, silence means, what is it? Consent to move on. Good. So trigonometric functions. Now, we're not going to get into the very hard ones, right? For those of you who will study calculus 2, and so, you'll get into trigonometric integration and differentiation. You want to know which world you are in. Right? So we know, all right, when we differentiated sine, you get cos. So if you integrate cos, you will get sine, right? Plus your k, of course. When you differentiate cos x, you had minus sine x. So when you integrate sine x, you will have minus cos x plus k, of course, right? Now look at this general formula here. If you have the integral of cos of some linear, right? Some linear function in the bracket, right? What do you get? Oh, and by the way, this function in here has to be linear. If it's not linear, you'll have to do other things, right, to integrate it. I'm not sure if this particular course is going to cover that. Good. So the integral, again, well, you differentiate, when you integrate cos, you get sine, right? So it switches to sine. Never trouble what's in the bracket. Put your k at the end here. But in front here, you have to divide the coefficient, which is 1 in this case. Again, doesn't have to be 1. It can be any number. You divide that coefficient by the derivative of the bracket, which in this case, it's a, right? That's your general formula. Remember, this formula only holds if whatever is in this bracket is a linear function. If it's non-linear, right, and you have like ax squared and all of that, no, this formula wouldn't work. There's something else you got to do, right? Which, as I said, is not covered under this course. Good. So where are we? Integrating exponential functions now. It's burning me with this computer one. And this is one of the easiest integrals, right? Because when you differentiate e to the x, as you see here, you get back e to the x. So if you integrate e to the x, you will get back e to the x plus k. Right? Remember your k at the end here. Right? So this is very easy, very easy. And of course, they extend it here. If you have a number in front of e to the x, you integrate it, you get back the same thing plus k. Right? Now, what about if you were to have e to the, not just x, but a linear function? Oh, and again, in the power there, you cannot, if you have function like ax squared plus b, no. Or ax cubed plus b, you can't integrate using this formula. Whatever is up there has to be a linear function, right? Keep that in mind. The minute that is non-linear, again, as I said, as a matter of fact, integrating e to the x squared is actually an unsolved problem to this day, right? If you have nothing to do with your life and you want to spend your life solving that problem, go right ahead. Right? So in this case, the integral of e to the ax plus b is equals to, write back the same thing, e to the ax plus b plus your k. But in front here, you must have 1 over the derivative of up here, which is a. So you get 1 over a. Again, if you have a number in front here, instead of 1 here, you have that number, right? If you have 2 in front here, then the 2 will be on top here, right? And we have some examples here, right? Integral of e to the 3x dx is equals to, right back the same e to the 3x plus k, but then in front you have the 1 that was in front here divided by the derivative of 3x, which is 3. Here, look at this one. Oh, and this is an example where the coefficient of e is not 1, right? It's a number 2. Good. So again, you write back e to the minus 5x, never trouble that, plus your k, but in front of it, you have to have what? The 2. Well, you're supposed to divide, right? You're supposed to divide by 1/5, which is the same as multiplying by, sorry, you're supposed to divide by minus 5, but it's the same as multiplying by minus 1/5, right? Same thing. I know you're seeing division here, but you're seeing a multiplication, but multiplying by minus 1/5 is the same as dividing by minus 5, right? As you know that from your little bit of fractions and so. Right? I'm not hearing anybody questioning nothing, man. Good. So we're looking at an exponential function still. And I remember when we had to differentiate something like a to the x, we couldn't do it directly. We had to change the what you call it? We had to change the base to e to the something, right? E to the z. And then we were able to differentiate. Well, same thing here. When we're integrating something like a to the x, we have to convert it, right? We have to convert it to e to the something, right? And here, look, a to the x. Look here, a to the x. It's equivalent to e to the x ln e, right? So when you do the conversion of that. So the integral of a to the x is equivalent to the integral of e to the x ln e, right? And using the formula we just learned, well, you write back e to the x ln a plus k. But in front here, you have to divide the 1 by the derivative of up here, which is ln a, right? And from that, they came up with this general formula that the integral of a to the x is basically 1 over ln a to the x. Of course, your plus k has to come there, right? So I mean, if you could memorize all of these, it'd be good. And y'all are young people, right? I want you to be using your memory, right? When I was a kid, your age, formula, you know, I look at the teacher chase you out of the class, they find you with a formula sheet. Have to know everything in your head, right? Memory is a vital cognitive ability you have, right? The day you start losing your memory, you're old, right? So y'all are young people. Good. So look at this one. I wonder why this is here. Well, it's scratching up about here. The integral of 1 over x is simply ln x, right? Simple as that. Of course, if you have maybe a c there, well, the answer is going to be c ln x. And of course, you got to put your k, right? Always got to put your k. So that's another standard formula, right? If you have not just 1 over x, but a whole, well, oh, again, this has to be a linear function. The integral of 1 over ax plus b, it's, okay, ln of ax plus b plus your k. But what do you put in front here? 1 over the derivative of what's in the bracket here, right? Which is a, 1 over a. Of course, this doesn't have to be 1 up here. It can be 2, it can be 5, it can be a minus number, all kinds of things, right? In this situation, you have 1, right? But look here, look here. The integral of 4 over x, right? Is going to be 4 ln x because it's just 1 over x, right? You can pass out this 4 outside here too, right? Here, the integral of 1 over 2x plus 5, you write ln of 2x plus 5, never change that, plus k. But in front here, you take this 1 and you divide it by the derivative of this, which is 2, right? So 1 over 2. Here, okay, and now you don't have 1 in the numerator. The integral of 3 over 4 minus 2x, you write back ln of 4 minus 2x, never trouble that, the modulus of it, plus k, right? But what do you put in front here? This 3 over the derivative of this here, which is minus 2, right? That's what you see here. Right? Any questions so far? Quite a bit of formulas, and so you want to memorize, but again, as I said, you do 10 of them, becomes second nature to you, man. Good. So let's pause there a little. Then we'll let me see. It's 4:03. All right. Let's pause a little. Let me just switch slides. All right. So we're doing some, heavier integration now. We're going to attempt to integrate products, right? So one of the things, what they're saying in all of this, right up here, is that you can use recognition sometimes, right? You can look at something, you can see that, you know what? Well, look at this function here, right? You can see that had you e to the x squared, if you were to differentiate that, you'll get this, right? 2x e to the x squared. So when you integrate that, if you recognize it, watch, whatever is in front here is actually the derivative of the power there. Then the integral is just going to be e to the u, right? And that's what you see here. 2x is simply the derivative of x squared. Therefore, the integral of this is going to be e to the x squared, of course, plus k, right? And it's as simple as that. There are times when you can just watch something and tell the integral. Most of the time, though, that's not going to be the case, right? And you have to kind of make use of some other techniques, right? Some other techniques that will help you to, do the integral, right? Again, as I said, in this course, we're not going to be dealing with, how would I say? We're just scratching the surface when it comes to integration, right? And in particular, integration of products and fractions and all of that. We're just going to scratch the surface, right? So this is one of the techniques. The technique involves changing the variable, right? So here it is. You want to integrate. What are we integrating here? We're integrating this. Oh my. There's something wrong there. No. Yeah. We're integrating this here. We're integrating this. And you want to know when you watch that alone, how on earth are you going to integrate something like that? And there's this method where they refer to as changing the variable. In other words, you want to see if you can rewrite this expression in terms of some other variable that will make it a little simpler, So here we have it. we're making the substitution u equal x cubed plus 5, right? So basically, let me just say, this here is the function x squared times x cubed plus 5 to the half power, right? So usually the u substitution is what's inside here, right? You usually take what's in the bracket there and let that be the u substitution. And just a little bit about how do you know that u substitution will work? It doesn't always work. It doesn't always work, right? When do you know that it will work? You know that it will work if the derivative of inside here is either a multiple or submultiple of what is in front here. So if you watch this thing, this is the derivative of in here is 3x squared. That happens to be a multiple of x squared, right? It's 3 times, right? 3 times x squared. So in this case, because the derivative of inside the bracket is a multiple of what's outside, u substitution or change of variable works, right? That's a little clue there I'm giving you as to when it works. Good. So what do we do now? So we do this u substitution, u equal to what's in the bracket there, right? X cubed plus 5. From that, you can see that du dx is equals to 3x squared, right? That isn't hard. If u is this, du dx is 3x squared. So what we do here, we separate the variable. And you see that the operator du is equivalent to the operator 3x squared dx. So what we're going to do now, we're going to try to write this thing. We're going to try to write the original thing now, right? Using 3x squared dx. And then because this here is du, we're going to replace all of this with du, right? And we're going to try to see if we can replace the rest with just u's. So at the end, your function that you are integrating will only involve u, right? But it must be simpler to integrate. Good. So, all right. So 3x squared dx, we put it here. How can we write this? How can we write this? Using 3x squared dx. Well, watch it. If we were to take 1/3 of x cubed plus 5, right? X cubed plus 5 to the half power, right? 1/3 of it. This 3 and a 1/3 wouldn't cancel out, right? And you will get x squared as you see here, dx as you see here, right? So remember, we can replace all of this now with du, because du is equivalent to 3x dx. X cubed plus 5 is u. Put u to the half. Bring this 1/3 here. So we now have a simple function to integrate. We have a function u to the half power. We could now integrate u to the half, which is not easy, right? Did I say not easy? I say it's very easy. Sorry, right? You'll have, okay, you add 1 to the power, it becomes 3/2, and you divide the 1/3 by 3/2, which is the same as multiplying by 2/3, right? And you multiply that, you get 2/9. You replace back u with x cubed plus 5, and then put back the power plus k, right? So what you were able to do, you were able to integrate this very complex thing in terms of u. Look here, right? You can integrate it in terms of u, which is much simpler. Think you're getting it? I remember the students, some past students, they like this method. I just want to show you an alternative to what is done here. Somehow they like that better. And every time I show them this, they don't like it. They say this is much harder to follow. So this is what they do. I'm going to erase all of this. I just want to show you what they do. All right. So down here, they take this here, right? All right. They take down here. And they divide both sides by 3x squared, right? So you have du over 3x squared is equals to dx, right? And what they'll do now, they'll write this, let me just show you here, they'll write this part here, right? So they'll have, I'm moving over here because the space is here. They will have x cubed plus 5, oh, sorry, yeah, to the half. I'm writing this here, x squared, right? Times du over 3x squared, right? So they're writing back this expression, right? In terms of, if they're putting where you see dx here, they're putting this, right? And what they usually do, they'll cancel this x squared, they'll cancel that x squared. And this expression becomes this now, x cubed plus 5 to the half power du over 3. And they'll take this 3 now to the front, and you have 1/3 x cubed plus 5 to the half du. And then they'll replace this now with u, right? So they'll put u here to the half du, right? So they seem to like that. They seem to like that. But your whole objective here is to rewrite this expression here, right? In terms of u. That's what you're trying to do in the entire thing. And once you get it in terms of u, usually, whatever you write, look here. This is very simple to integrate. Don't be scared by the fraction, right? But it's much simpler than that, than what you had to integrate at the beginning here, right? Much simpler. I think there might be an example or so more. Let me see. Okay, look at this one. So you want to integrate this thing here, right? Very horrible looking function, right? So when you watch this is the same as this, right? So there is a function in here. And indeed, when you differentiate sine x, you get cos x. So this is perfect for u substitution, right? So we let u be sine x, which implies that, well, you kind of skip out a step here. Du dx is equals to cos x, right? And then you take this x over, this dx over here, right? And that's how they get this. The textbook writer just jumped the step. So we have to now write this here in terms of, okay, cos x dx, right? And that's not hard. It's just like this cos x dx, we put it here. We know that all of this is simply du. This here is u to the third power. So when we integrate that, you get u to the 4 over 4 plus k. And then you write back what is u, which is sine x, right? So that's your answer. So that's u substitution here. Good. So this is another method now that you can use to integrate products, right? It's called integration by parts. And as I said, we are going to do the very, very, very basic, right? Integration by parts can get very crazy, right? But we are going to, as I said, do the very, very simple ones, and the ones that you can get in just one, let's say one stage. They have what you call, you have to integrate things by parts. You have to do it repeatedly and all kinds of things you got to do. Don't worry about all of that. Right? Even the notes I'm going to send you, you're going to see some very complicated ones. Leave that for a higher course, right? Good. So look at this one. So, and I'm going to state without any proof here, right? That if you were to integrate something like this, v du dx, with respect to x, it's equivalent to uv minus the integral of u dv dx, right? Good. Now, what's the idea in this one, right? The whole idea is that if you have something of the form v du dx, and you can somehow get what is u, well, you already know v here, right? So that's no problem here. If you can get u and somehow u dv dx is something simpler to integrate than v du dx, well, then that will lend itself to our being able to integrate such functions, right? Here's an example. You have x e to the x, right? Now, oh, and by the way, even though this, let me just warn you, right? Even though this problem, in this case, the function is set up in such a way, you have x e to the x, and right away, we make the substitution that v is equals to x. You notice that here. And du dx is the same as e to the x. Not always is that the case. Sometimes the v is the function behind here, and the du dx is the function in front here. This one, it so happened that the x in front is the v, and the e to the x is the du dx. As I said, I'm warning you, not always will that be the case, right? What I want to tell you also, and that's very reassuring here, is that this particular method actually indicates to you that you are going down the wrong road. The minute you see that what you end up with later on is more complicated than what you started with, you don't know that, you know what, I made the wrong substitution, right? It will tell you, right? It will tell you. Anyway, let's deal with this. So here, all right, the x is the v. So you notice we will need the v dx, which is 1, right? So if v is x, then dv dx is 1. And if du dx is e to the x, then u is also e to the x, because the integral of e to the x is e to the x. So we're putting all these things now in this formula, right? Good. So we know this part, right? This part is this. The formula calls for u times v, right? So this is u, this is v. So you get e to the x by x minus the integral of u, and what's u? E to the x times dv dx, which is 1. And you see what I'm saying here? The integral of e to the x times 1 is really e to the x, right? The integral of e to the x is e to the x, which is easier to integrate than x e to the x. So this method perfectly suits this kind of integration. So the integral of this is equals to x e to the x, you write that back. And the integral of e to the x is e to the x. So you put that back there, plus your k. Right? And if you want to, I mean, e to the x is it's common, so you just put it in front, that's no problem, right? So this kind of a function lend itself to this here, right? Being used to integrate it. What you can do in your own time, if you deliberately switch this around and say, let this be du dx and let this be v, and try the same method and see what happens, you will see that you will end up with something very complicated in here that is harder to integrate than what you started. And you know what? I made the wrong substitution. Right? Try it on your own. I don't have to do it for you. When your own sweet time, try it. Look at another example here, right? You want to integrate. Oh, and this is a good one. This is a good one, right? Remember we said okay, the integral of v du dx is equals to uv uv minus the integral of u dv dx, right? So I left out the dx here and a dx here. All right, good, yeah. So we said that. So watch here. In this case, this x to the 4 doesn't match the v, right? And the ln x doesn't match the u dx. Instead, the ln x is the v, and the x to the 4 is the du dx. So the way this function is laid out is not okay that x to the 4 is v, no. Right? Nor that ln x is du dx, no. And I'll tell you what, and again, if you were to, in your own time, you try it, you let x to the 4 be v, right? And ln x be du dx, and you will see that it will take you down a rabbit hole, right, of confusion and worries and all of that, right? And you will know that, you know what, I'm going down the wrong path. Look how things are getting harder as I go on. Right? And you'll know, no, let me backtrack. I made a mistake, like, so talk about it, right? In this case, and again, this is textbook writing. The lady who wrote, there are two ladies who wrote this book, right? And that I'm using here. So they will try it that way and say, oh God, no, that is leading us into trouble. Let's switch around. And that's what they did here, right? So the V is the ln x at the back, and the du dx is x to the 4, right? So here, okay, V is this, so dv dx is 1 over x. Du dx is x to the 4, and you end up with 1/5 x to the 5 as u. And we put all of that in our formula here now. So u times v, that's what is here. All right, you don't have to do nothing with that. And here we have to integrate now u dv dx, right? Which is this times that. So when we multiply this by this, look how it looks ugly here. But when we simplify it, that's what we get. Right? And that's easy to integrate. Right? It's like you bring this 1/5 in front here, right? But x to the 5 multiplied by 1 over x is really x to the 4, which is easy to integrate. Right? So this integral is equals to this minus, well, the integral of that, which is that, right? And I'm not going to go any further with integration by parts. As I said, if you were to study calculus to a higher level, man, when you see me back, you say, sir, you're doing all them easy thing, man. Right? Because, as I said, integration and differentiation, it's a whole branch of mathematics. So what else would you expect? Oh, and this is the last one to show you how, I'm not going to go through it, right? But they showed you how they were able to, because this was a problem, how to integrate ln x. We know how to integrate 1 over x, but how do we integrate ln x? We don't know. So some smart Alex says, let's treat ln x as 1 times ln x. So they let v be ln x and let du dx equal to 1. And with that, I'm not going to go through the example. With that, they were able to integrate ln x, right? And the integral of ln x is this here. And that was a remarkable, I mean, whoever came up with that idea, and sometimes you see these things are simple, but you never know how long they were puzzled by how do we integrate ln x. And some smart Alex says, well, why not treat it as a product? 1 times ln x. And it did work, as you can see in this example, right? Good. So we're going now to integrating fractions. Right? We're integrating fractions. And again, we can only scratch the surface of fractions, right? And we're going to just talk about some general types and some general approaches to integrating fractions. So this is the first type. If you ever were to see an integral of some fraction where the numerator is the direct derivative of the denominator, well, the integral is ln of what's in the denominator, right? Simple as that. So this is a standard result. And in other words, you can do this by recognition then. You could watch the thing and say, you know what? Oh, I could figure out what the integral of this fraction is. Right? Note, the numerator is the derivative of the denominator. Right? As an example, when you watch this, the derivative of 1 plus sine x is cos x. Therefore, the integral of cos x over 1 plus sine x is ln of 1 plus sine x. And don't forget your k at the end. Right? In this case, look here. This here, all right, the derivative of the denominator is 3x squared. So it's not exactly x squared, but if I were to take this 3 and multiply it by this 1/3, right? That will give me my x squared there, right? Isn't that so? So in other words, indeed, right? The integral of 3x squared over 1 plus x cubed is really ln of 1 plus x cubed. And 1/3 of that will give you this, right? Will give you that. Another example, same thing here. You differentiate in the denominator, you get exactly what you have in the numerator. So that's your answer, right? So the recognition aspect is so important, right? This one is a little puzzling. Spend some time with it. Type 2 now. Changing the variable. Yes, you can change variable even with fractions, not just products, right? Good. So look here. And again, oh, by the way, change of variable will only work if when you watch what's in the bracket at the bottom here, the derivative of it is either exactly what's on top or a multiple or submultiple of what's on the top, right? And you can see that the derivative of the bottom is exactly 2x. So change of variable should work perfect here. So we take what's at the bottom, that's your u substitution always, right? What's in the bracket there. And from that, you get du is equivalent to 2x dx. So we are writing back this expression here with this 2x dx, right? Somehow. So 2x dx over this here, right? What's that equivalent to? Remember, 2x dx is the same as du. And at the bottom here can be written as the root of u. So you have something very simple there to integrate. If you don't recognize what this is, right? This is basically the integral of 1 over root u du, right? If you just can't recognize that. And this can be written as that. And, well, don't be scared by the negative and the fraction, right? You add your 1 and you divide the number in front here by whatever that is. And you get this, right? Plus your k, of course. So writing back, what is u now here, right? You get back your integral. Good. Look at this one. So in your denominator, this is the same as this, right? Cos x over sine x to the 4th power, right? So the derivative of this is exactly that, right? So in other words, it's a perfect candidate for u substitution, right? And from that, then if you let u be equal to sine x, this function inside here, then du is equivalent to cos x dx, right? So we're writing back this function here, this here, in terms of u now, right? So this here matches up du, and 1 over sine to the 4, right? Sine x to the 4th power is u to the 4. And you integrate that, you get that, plus your k. And then you replace back u, right, with sine x, and you will get that. Note, your k does not always have to be at the back there. Note where the k is this time, right? I remember doing that in a multiple choice, and people said, sorry, but the answer in there, because they're looking for something plus k, right? I was even asking them, why can't I write something minus k? What's wrong with that? Well, and then finally, there's a last type, right? The type that involve what we call partial fractions, right? We did that when we were doing differentiation already. So I don't have to show you how I got from here to here, right? So you use your knowledge of partial fraction. Split this up into two parts. So the integral of this is equivalent to the integral of that minus the integral of that, right? And that's what you see here. And we know how to integrate this, right? Is the ln of that. We know how to integrate that. Is the ln of that. And then using your knowledge of logarithms, this can be rewritten as that, right? And you simply finish here. So that's what would I say? An introduction to integration. We're not going to go more than that. We're not going to go more than that. Next week, we're going to take some time and do some applications, right? Simple applications too, very, very simple. And well, that closes off our course. But so